So as you saw, some of the topics in this course, we start out with operations with numbers, which is pretty basic. I don't want to bore you by going over things the same way you saw them before. Now, of course, for you, since you had the 373 last year, it's going to be a lot of repetition the first few weeks. But stay awake and stay with us. So anyway, one of the biggest misunderstandings with math comes from the most basic concepts, because we don't take the time to understand why we do things or how things work. We're just told, do it this way. This is what you do. So I want to take some time to explain why things work the way they do as we go through these topics. So the first thing I'm going to look at is probably the simplest topic in math, but also the most misunderstood. And that is the concept of what is a number. So if I put a 4 up here, how many of you would tell me that that's a number? Show of hands. Most of you would, right? 4, however, is just a numeral. It is an amount. It's telling us how much. To truly be a number, it must have not only tell us how much, but of what. So we may have 4 cows. So now we have that amount, the 4, which I'm going to refer to as the count. That tells us how many. But we also have to know of what. In this case, that's cows, which I'm going to call the name. Every number has 2 parts, a count and a name. Now, this is not just my excuse for making you label everything with inches or feet or whatever. That's not my purpose here. But having the 2 parts of the numbers and seeing how they actually work in our basic math operations explains most of what we've learned in mathematics. So let's take a look at these 2 parts of a number and how they interact in our 2 most basic math operations. Addition and multiplication. Now you might be wondering, well, where did subtraction go? I thought addition and subtraction were our most basic ones. Well, addition and subtraction are really the same operation. In fact, if you get deep into number theory and math theory, subtraction doesn't exist. There is no operation of subtraction. It's just the reverse of addition. And the same with multiplication and division. They're really the same operation, just one's going forward and one's going in reverse. So anything that we define or any rules we state that apply to addition and subtraction, or that apply to addition, will also apply to subtraction. And the same with multiplication and division. Anything that applies to multiplication also applies to division, just in reverse, backwards. So let's look at a sample problem here. Let's take something like 4 inches plus 7 inches. What do we get? 11 inches. Good. So if we look at what happened there in terms of our count and a name. For our counts, we had 4 and 7. What happened to them? Yeah, we combined them. We added them to get 11. So we combined the counts. We're adding, so we combined them with addition. But let's look at the names. We had inches and inches, and what did we end up with? Inches. So when we add numbers and when we subtract, we simply keep the same name. Now you're probably looking at that thinking, yeah, that's different, but not that interesting. Maybe not quite worth your 400 and some bucks for the course yet. But let's take a look at multiplication and see how that's different. I'm just going to abbreviate inches, IN, times 4 inches times 7 inches. And what do we get? 28, but it's not inches now, it's inches squared. If you think about it, most of the time if we're multiplying 2 lengths, we're looking at an area where we have a length and a width that we're multiplying. So we had 4 and 7 are still our counts, and we still combined them. This time we're multiplying, so we combined them with multiplication. So we still combine the counts. The difference came in the names. We had inches and inches, and we ended up with inches squared or square inches. So when we multiply, we also combine the names. Now you're might be looking at this thinking, okay, I didn't really realize that before, but why is it such a big deal? Well, because all of the operations we do with all of our other forms of numbers follow this exact same set of rules. This explains how we work with fractions, decimals, algebraic numbers, scientific notation, everything. In fact, it comes right down to explaining what numbers we can actually even use in each different operation. For example, let's say I have 3 cows plus 5 boys. Do I get 8 cowboys? That doesn't work, does it? And now you may have heard the commutative property. You can switch when you're adding. You can switch the order of the numbers. So what if I had 5 boys plus 3 cows? Does that give me 8 boy cows? Anybody here with a farm background? You can tell me that's a whole bunch of holes. I know, long way to go for a joke. But there's a point behind it. Like I said, math teacher, stupid sense of humor. We get used to it. There's a point behind it. When we are adding numbers, we're going to keep the same name, which implies we must start out with the same name. Up here we had inches and inches, and we combined them to make inches. Here we had cows and boys. We cannot combine those with addition, because if they don't have the same name, we don't know what name to keep. Just like if we had, let's say we have 8 feet plus 2 pounds. If we go to add those, what do we get? Careful. If we go to add them, they have different names. We just get 8 feet and 2 pounds. We can't combine them with addition or with subtraction because they have different names. So when we add or subtract, we need to have the same name. Here's some circles. Now with multiplication and with division, because we're going to also combine the names, we don't have that requirement. If I have 8 feet times 2 pounds, I am going to combine the counts. We're multiplying, so it's 8 times 2 is 16, but I can also combine the names. Feet times pounds is foot-pounds, which is a unit of torque. Or if you're looking at construction, it's a unit of moment on your beams and stuff like that. It's a measurement of bending capability. Ability to support a bend or the amount of bending force on a beam. So when we multiply, we do not need the same names. So when we're going to work with numbers, this little rule tells us what we can actually use in each operation. So now let's go ahead and take a look at some of our other forms of numbers. Let's jump right in to everybody's favorite type of number. Fractions. Yeah, I saw the looks. If I asked people on the way into the classroom on the first day what they hated most about math, 4 out of 5 people would say fractions. So if you're one of those 4, don't feel bad. You're not alone, I assure you. Fractions is one of the most misunderstood topics in math. The other 1 out of 5 usually would say the teacher, by the way. So anyway, a little bit of review. What's the top number of a fraction called? The numerator. What's the bottom number called? Denominator. My pause there made me think a little bit. I am a horrible speller. I a lot of times get halfway through a word and forget how to spell it. And I also realize that sometimes when I'm tired, my handwriting leaves something to be desired. If anything ever appears up here that you can't read, don't be afraid to ask. I assure you it was intended to be English. I probably either really butchered the spelling or wrote it too sloppy to be readable. So I won't be offended if you can't read what I'm writing. So we have a numerator and denominator. Well, what does it mean to numerate? Every 10 years, our government sends out people to do a census, to numerate the population. What are they doing? They're counting. A numerator is a count. It tells us how many. Denominator, well, we have different denominations of money. We have different denominations of organizations, religious organizations specifically. To denominate means to classify or to give a name. So our fraction, numerator and denominator, is just a count and a name. So when people look at that 2/7 and they see two numbers, but it's not. It's a single number with two parts. Just like having 2 cows or 2 inches, here we have 2/7. The 7th is a name. When we get into fractions in more detail in a couple of days, we'll look at what does it mean to be a 7th. But for right now, we just know it's a name. So when we go to add, if I have 2/7 plus 3/7, way back in about 3rd grade when you first started working with fractions, when you went to add fractions, what did your 3rd grade teacher tell you? You must have common denominator. That's not a special rule for fractions. That's true for every type of number. To add numbers, we must have the same name. And in fractions, that's a common denominator. When we add fractions, you combine the numerators and keep the common denominator. Again, not a special rule for fractions. Every number, you add the counts, 2 plus 3 is 5, and you keep the same name, 7ths. Exact same rule as we would use for any other form of a number. Now, what if I had 1/3 plus 4/5? Can I add those the way they're written? No, right now they have different names. We would have to give them the same name or give them common denominators, which we'll look at again after a little bit more time. On the other side, multiplication, if I have 2/7 times 3/7, I combine the counts. 2 times 3 is 6, but I also combine the names. 7ths times 7ths is 49ths. What about my 1/3 and 4/5? If I did 1/3 times 4/5, do I have to have a common denominator to multiply? No, because any number I do not need the same name. Again, that's not a special rule for fractions. When I multiply, I just combine the counts. 1 times 4 is 4. And then I also combine the names. 3 times 5 is 15. So the same rules apply for fractions. I do not need the same name to multiply, and I'm going to combine the counts and also combine the names. Well, let's look at how this applies to decimals. .21, what's the formal way of pronouncing that? 21 hundredths, there we go. When we write it like that, now the count and the name becomes a little more obvious. We have 21 of something, and what we have is hundredths. So let's look at adding decimals. If I have my .21 plus .3, if I go to add that, is that going to work? What's wrong there? We've been told that we have to line up our decimal points. Why? 3rd grade teacher said so? Yeah? Okay. Well, it's the same reason. This is 21 hundredths, as we said. This is really 3/10. Right now, they have different names. But we can give them the same name by simply putting a 0 there. Now that is 30 hundredths. When we give them the same name, now the decimal points would naturally line up. And now you've always been taught when you add, you've got the 1, 2, 3 is 5. What do we do with the decimal point? Drop it straight down. Perfect. Again, it's not a special rule for decimals. When we add numbers, we keep the same name. Bringing that decimal point down keeps the same name. 21 hundredths plus 30 hundredths is 51 hundredths. On the other side of things, when we multiply 0.21 times 0.3, do I have to line up the decimal points? No, I don't. 21 times 3 is 63. Where does my decimal point go? Got to put a 0 in and then the decimal point. Why? You started to say it. You count, right? You count 1, 2, 3 decimal places in the answer, in the problem. So you go down to the answer and you count back 1, 2, 3 decimal places in the answer, right? Why? Third grade teacher said so. Good. Well, yeah, that's exactly it right there. When we multiply, we combine the counts, but we also combine the names. This is hundredths. This is tenths. Hundredths times tenths would be thousandths. So when we're counting those decimal places in the problem and making sure we get that many decimal places in our answer, all we're doing is combining the names. As you can see, all those special rules you were taught for all those different forms of numbers are really nothing more than different ways of making sure you combine the counts and also combine the names. Or if you're adding, you must start with the same name before you combine them, and then keep that same name. Well, since we're having fun, let's keep going. Algebraic numbers, 4x. A lot of people start to get nervous when they see the x come in. Letters in with our numbers. But 4x is just a number like any other number. We have a count and we have a name. Just like having 4 cows, 4 inches, even 4 sevenths. Here we have 4 x's. The difference is we know what a cow is or an inch or even a seventh. We do not know what an x is, but it doesn't change how we use it. If I have 4x plus 9x, I get, perfect. I combine the counts. 4 plus 9 is 13, and I keep the same name, x. If I had 5x plus 2y, what do I get? It's 5x and 2y, exactly. Just like when we had 8 feet and 2 plus 2 pounds, we could not combine those because they had different names. 5x and 2y have different names. We cannot combine those with addition. However, just like with our feet and pounds, let's look at 4x times 9x first. 4x times 9x becomes, well, we combine the counts. 4 times 9 is 36. But we also combine the names. Just like inches times inches became inches squared or square inches, x times x becomes x squared. And for our 5x and 2y, if I'm multiplying 5x times 2y, it doesn't matter that they have different names because we're multiplying. We don't need the same name. We're going to combine the counts. 5 times 2 is 10. And also combine the names. X times y is xy. Just like feet times pounds became foot pounds. What do you think? Like I said, probably not groundbreaking material yet, but hopefully a little bit different way of looking at things than what you've seen before. So the next question is, how does all of this tie into what you do every day? Don't work with a lot of numbers like 3 plus 4. We work with a lot of bigger stuff. Well, the concept that ties it all together is the concept of place value. Just like a number, it's another one of those concepts that's very simple and very basic, but way more powerful than we give it credit for. So we're going to start at the end of a number and work our way backwards. What's this last place value here at the end of a number called? Careful. That's the ones, right? The next one back is tens. And then hundreds. And those are actually our only three place values. Those three place values are repeated over and over again. Ones, tens, hundreds, ones, tens, and hundreds, and over again. This is what we call the thousands group. This is the millions group. Then, of course, we go on to the billions and the trillions and the quadrillions, quintillions, blah, 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 blah. In practicality, the only time we even get up into trillions is when we start talking about the national budget, national debt, and stuff like that. So, millions and billions is as high as you should ever need to go. And, of course, this is the base group down here, the first three. When we name a place value, we name the place value and its group. So this here would be just the tens place. This would be the 10,000s place. This would be the 10 millions place, and so on. Now, I'm not going to spend a lot of time with you on how to read a number, but I am going to put up this. 2,758. Again, I'm going to just assume you guys know how to read that off. But 2,758, as we're used to seeing it, is not the full form of that number. That is an abbreviation. The only reason we know that this 7 is 700s is because of its location. It's in the hundreds place. But the full form of this number is 2,000s and 700s and 5 tens and 8 ones. If we get into algebraic numbers, you'll see that those are actually the same thing. They're just written out. They're always written out in their long form. This is sometimes called the expanded form of a number. In reality, it's just the full form of the number. It's no longer abbreviated. Now, because of what we're used to seeing being an abbreviation, and those place values telling us, replacing the word thousands, hundreds, and tens and ones with just the location of the digit, that was actually what created the need for the invention of a zero. If I have 200s and 9 ones, but what's missing there? Yeah, the tens, right? Do I need to put and 0 tens when I write it out? Well, not this way, because it tells me what those values are for each of them. But if I'm going to abbreviate it like this, I do have to put 209. That 0 is just holding that location to tell me the tens were empty. There were none in my, if I wrote it out in long form. That 2 is hundreds and not tens. Why is that so important? Well, when we go to add, subtract, multiply, and divide, that will define how we do things according to what we just talked about earlier. We're a little bit early today. Normally at 1:20 we will take a 10-minute break, but this is a good spot to break here before I launch into the next section here. So we're going to take our break right now. Let's come back at 1:25.